Okay, so in this video, I'm just going to do a little stop on the progression and do like a little summary. So far, let's see. We have defined the first principle of thermodynamics. With the equation Q minus work will be equal to the change in energy. Okay? In most instances, we say that the change in energy is change of internal energy plus change in kinetic energy plus change in potential energy. But in most cases, let's say we neglect these two, the potential and kinetic energy. So we have that Q minus the work was equal to the change in internal energy, where the work was equal with the sign convention we decided to PdV. Okay? So really these are the two equations we have been using most of the time. Then I kind of mentioned that for a closed system, the change in internal energy could be equal to mCv delta T, or mCv T2 minus T1. So that's what we had. And where Cv was defined as being the specific heat. Alright. So now what I want to add is that for a control volume, we went and we did rewrite the first principle of thermodynamics, but this time in function of time. So we had heat transfer Q minus power plus mass flow enthalpy going in was equal to mass flow times enthalpy going out. Okay? So in this case, if you want, we have Q minus power equal to M H out minus H inside, which will be equal to M dot delta H. So this is what is new now. For a control volume, the same thing we had over here, the internal energy, you could rewrite this as M, but instead of C sub V, you write C sub P delta T. So this would be equal to M C sub P T2 minus T1. So what is important here for you to remember is that for closed systems, you always be dealing with internal energy, and this is the general expression, but in the cases of an ideal gas or ideal substance, you can write this as mc sub v delta T. For a control volume, or what I like to call an open system, you deal with enthalpy, can be lowercase or really should be uppercase over here, will be equal to what? H2 minus H1, or mc sub P delta T. So that's where you need to be careful. Internal energy will always be related to C sub V. Internal change in enthalpy will always be related to C sub P. Okay, so since I mentioned C sub V and C sub P, let me try to give some relations. So K is C sub P over C sub V. This is a gas constant. Ratio of the specific heat at constant pressure over the specific heat at constant volume. Cv is always higher than Cv. And by definition, you have that Cp is equal to Cv plus R. So actually using those two relations over here, you can write different relations. So let's maybe derive one. So let's say that using K equals Cp over Cv, that's going to give us that Cp is equal to K times C sub V. So now, if we replace over here, what do we have? We're going to have C sub V plus R will be equal to K C sub V. So this would give you C sub V factor of 1 minus K will be equal to minus R. Or when I go to the next page, we will have that C sub V to be equal to minus R over 1 minus K, or C sub V will be equal to R over K minus 1. And now we just go back to the relation K equals Cp over Cv. So another relation for Cp will be equal to what? K R K minus 1. Okay, so before I mentioned that these relations will be true for an ideal gas, but I like to extend it to an ideal substance. So let me try to define ideal gas or ideal substance. So what we know about the ideal gas is what? So the first one, it will always obey the relation PV equal RT, or PV equal nRT. Okay? But what's important about the ideal gas is that it always remains in the gas state. So I like to extend that definition to, let's say, an ideal substance. So in some problems, sometimes it's just easier to use that assumption, but you don't have to. So how do I define an ideal substance? An ideal substance would be substance that remains in the same state. So for example, if we are talking about water, water can remain in the liquid state, or water could remain on the gas state. Okay, but the other is another condition. So the state needs to be as far as possible to the saturation lines. That sounds very difficult, but if I do a figure, I think it will make sense. So here this could be the PT POV diagram, and over here, what do we have? Remember that curve where in here is a mixture, in the middle here was a mixture, so this one is not going to count. Here can be superheated oil gas, and here will be a liquid. So what I'm trying to say is that if the state is really close to these lines, the saturation lines, so this side was saturation, gas, saturation, liquid. If the state is very close to this line, the assumption is not going to be that good. But if we move far away from this line, from the saturation line, then the assumption becomes better and better. Okay? So this will be all for this video. Thank you for your attention.